Okay, so let's talk reabsorption. So what we've just talked about is that we filter out an enormous amount of liquid here at the glomerulus. If we were to track it, that would be, if we tracked how much fluid came to this point, it would be something like 180 liters per day. That's our glomerular filtration rate. Now, typically a person will only urinate somewhere a little less than 2 liters per day. So 180 liters per day passes this point, but 2 liters per day actually gets to this point. So where does the rest of it go? What about the other 178 liters every day? And the only answer can be it's reabsorbed. It's got to leave the tubule and go back into the blood. So let's take a quick look about where that happens, and then we'll talk about how it happens. So first, after the Bowman's capsule, we're going to hit the proximal convoluted tubule, where a lot of reabsorption happens. By the time we're done with the proximal convoluted tubule, if we were to look at how much actually goes past this point, it would be about 60 liters per day, which implies that between here and here, we reabsorb a lot. If I've got 180 liters per day that cuts to here, but 60 that gets to here, that implies that I have reabsorbed something like 120 liters each day, which is about 2/3 of this. So roughly 66% of what got filtered gets reabsorbed in the proximal tubule. Now, as I go through the loop of Henle, by the time I get to the end of the loop of Henle, I'm only going to have about 20 liters left at this point. So between here and here, that means I'm going to reabsorb more. That means another roughly 40 must be reabsorbed at that point, which is pretty close to about 20% of the total. So what's left by the end of this is somewhere around 10% that's left. Now, if 20 liters a day gets to here and about 2 liters a day gets to here, that means we're still reabsorbing here in the distal tubule and the collecting duct. But the difference is that up until then, the proximal tubule and the loop of Henle, that absorption doesn't really change. That's obligatory reabsorption. No matter what else happens, we will reabsorb that roughly 120 liters a day here and 40 liters a day along here. What happens after that, though, is variable. So the PCT and the loop are obligatory. How much we reabsorb in the DCT and the collecting duct, that's variable. And it's under the control of a couple of hormones, mostly under the control of the hormone aldosterone and the hormone vasopressin. I usually call it vasopressin, but it's also known as antidiuretic hormone, or ADH. So, based on how much aldosterone and vasopressin my body is making, that will adjust how much I reabsorb in this area, from just a little, in which case I would end up with more than 2 liters a day of urine, or I reabsorb a lot, which means I would end up with less. This can get as low as, in a healthy but dehydrated person, that could be down around half a liter a day, 500 milliliters. And if you're drinking a lot of water, it can be significantly more than 2 liters a day. So, all of that is going to be under the control of these two hormones. We're going to talk about those in more detail a little bit later, but just very briefly, aldosterone increases water and sodium reabsorption, mostly in the DCT and the upper part of the collecting duct. Vasopressin increases water reabsorption, mostly in the rest of the collecting duct along here. So we're going to talk in some detail about the details of how those work in a little bit. But what I want to do next is go over the mechanisms for how we do reabsorption here. I did just kind of briefly want to talk about some of what gets reabsorbed. So here in the PCT, we're going to reabsorb as much glucose as we can. Assuming that your blood glucose is normal, you should reabsorb all of the glucose that you filter here. In fact, if you don't reabsorb it here, it's going to come out of the body because this is the only area where we can reabsorb glucose. Any proteins that got filtered should also be fully reabsorbed. So these two should be completely reabsorbed at the PCT. You also get some reabsorption of sodium, potassium, chloride, bicarbonate, calcium, and water. There's other things too, but those are the ones I'm going to mention here. So that's in the PCT reabsorbs a lot of stuff. There are a few things secreted here too, notably H+, but we'll get to that. Now, in the descending part of the loop of Henle, the part going down, here we reabsorb water. And in the ascending side, the part going up, we're going to reabsorb mostly sodium, potassium, and chloride. The reabsorption of those two plays on each other, and that's going to be a very important thing when we talk about fluid balance in the third lecture of the urinary system. Now, up here in the DCT, we're going to reabsorb sodium and water. We're actually going to secrete potassium here. Potassium is going to end up moving into the tubule, but we'll talk about that when we talk about how aldosterone works up here. And then in the collecting duct, we're primarily going to be reabsorbing water. Now, I'm not mentioning urea along here, although it is important, and if you study this in the future, you will learn more about urea. Today, I'm going to be sticking primarily with sodium and water, a little bit of potassium, and a little bit of glucose as we go. So let's talk about some details of how reabsorption works here in the PCT. When we're talking about reabsorption in the PCT, while a lot of things get reabsorbed here, I'm going to focus on a few things in particular. So as we're talking about this here, I'm going to be focusing on reabsorption of first sodium, and then glucose, and then water. So that's how we're going to direct this. Now, to start with, we need a little bit of terminology. So if you imagine that we're looking at the proximal tubule here, if I were to take a close-up of the wall, I might see something like this. So these are the individual cells that make up this wall. The wall of the tubule is made up of a single layer of cuboidal cells. They're joined to each other by some kind of leaky junctions that allow water and some ions to pass through. Inside the tube, this area in here, we call the lumen of the tube. So this is inside, this is outside, this is where the capillaries would be. And we use specific names for the membranes of these cells. Here on the side of the lumen, we call this the apical membrane. This side out here we call the basolateral membrane out on this side. So in order for something to be reabsorbed, it's got to get from the lumen out here to where the blood vessels are. In other words, it's got to get from here to here. So that means it has to pass through both the apical and the basolateral membranes, or go between the cells in the case of water. So we're going to look at three particular solutes here: sodium, glucose, actually two solutes, and then the solvent, water. So I'm going to draw a large cell here. This down here is its apical membrane, and up here is the basolateral membrane. So this side. So this here is the lumen, which means anything we're reabsorbing starts here and then has to go through the cell to get out to this side. This is outside the urinary tubule. So let's start with sodium. So our situation is that I've got sodium in here, and I want to get it to here. Now, sometimes the question comes up, well, couldn't I just put some sodium channels here, and then sodium could just diffuse through the cell? If you put just simple sodium channels here and here, then sodium would diffuse through the channels, but it would only do so until it reached equilibrium, until the concentration of sodium was the same here, here, and here. At that point, there wouldn't be any overall movement of sodium anymore. So that really wouldn't do it. We want to get sodium moving through this cell. We're going to end up reabsorbing something like 2/3 of the filtered sodium here in the PCT. So I need something a little more active than that. I'm going to accomplish that. I will have simple sodium channels here. So this is just a regular sodium channel, like a leak channel. Sodium can pass through that either way. But up here in the basolateral membrane, I'm going to have sodium-potassium pumps. So these are active ATPases. If you remember how these work, these take 3 sodium and move them out of the cell in exchange for 2 potassium moving into the cell. They use ATP to do that. Excuse me. Now, by actively pumping the sodium out, they're going to make sure that the concentration of sodium inside the cell is very low, lower than this. So I'm going to demonstrate that by making the sodium label in here small compared to this, indicating that, so that S says Na+ if you can't see it, indicating that there's a concentration gradient here from high to low. This continually pumping this out makes sure that stays low. So that means that most of the sodium movement here will be inward through those channels. So sodium's overall direction of movement is this way, pumped out here, which kind of sucks it in this way, which means we get reabsorption of sodium. Yay! Now the question also comes up, so what about this potassium here? What happens to that? These cells have leak potassium channels on this membrane, which means the potassium can just move right on back out again. Now, since there are no potassium channels here, as this potassium gets pumped in, its concentration rises and it's going to tend to just come back out. That does mean that overall we're getting more positive out here as we move sodium this way and potassium just sort of cycling. That actually helps to draw chloride from the lumen out here, but we're not going to worry about chloride right now. So, overall what we've done is reabsorb sodium. Now keep in mind, this concentration here is staying low as this pump works. That's going to be important in a moment. All right, so that's sodium. Now let's talk about glucose reabsorption here in the proximal tubule. This question again comes up. If I just had glucose transporters on the apical and basolateral membranes, passive glucose transporters, then glucose could diffuse through, but it would end up equally distributed. And I want to get all of the glucose, at least as much as I possibly can, from the lumen to here. I don't want to have any glucose left in the lumen if I can avoid it. Now, the problem, then the question is, well, okay, let's put a powered glucose, a glucose ATPase up here, just like we did with sodium. And that would be a great idea if we had a glucose ATPase. But as far as I know, there is no such thing. Since we don't have a powered glucose transporter, we're going to have to get clever about this. How can I get active transport of glucose without an active transporter? Well, if you remember, way back in the beginning of the class, we talked about a concept called secondary active transport. Here's where that's going to come in handy. All right, so we're going to start with a situation where I've got glucose in here, and the concentration of glucose inside is maybe a little bit higher than outside. So this is slightly smaller than that, meaning that glucose doesn't have a very strong concentration gradient. But if it has one, it's actually this way, which is the direction we don't want it to go. So how can I make sure that glucose is going to be moving this way against its concentration gradient? That is actually going to be the job of a co-transport. What we're going to have here is the SGLT, which stands for sodium glucose luminal transport. I'll write that up here in case you want to know. Sodium glucose luminal transport. The SGLT. The SGLT is a passive SIM port. Sodium and glucose pass through it as long as they do so together and in the same direction. The easiest way that I know of to think about it is to imagine sodium and glucose bouncing around out here, and then to think, in order to go through, they both have to arrive on the same side at the same time. So if it's just a glucose, nothing happens. If it's just a sodium, nothing happens. But if they both get there, they both go through. Likewise on this side, just a glucose, nothing. Just a sodium, nothing. Both, they go through. Remember, that's the idea of a sim port. So let's think about which way that's going to work. So if I just look at the glucose, there's a slightly higher concentration here than here, which means glucose is more likely to be on this side than this side. So glucose alone is a little more likely to bump into this side of it than this side. But it doesn't work unless the sodium is there too. And look at the sodium concentration difference. Sodium concentration in the cell is very low, which means the chance of a sodium bumping into this side is very low. The chance of a sodium bumping into this side is much higher. So, yeah, glucose is a little more likely to be here, but sodium's a lot more likely to be there. So the side that's more likely to get them both together is the outside. So sodium and glucose will more often be together on this side and move in than on this side and move out. And that's primarily because this sodium concentration is so low. Because of that, most of the sodium and glucose movement through the SGLT is inward, even though that's against glucose's concentration gradient. That's why we call this secondary active transport. It is active transport of glucose, but it's through a passive transporter. No ATP is being used here. We'll come back to that in a moment. So once the glucose is in here, now what happens to it? Well, over on this side, all we need is just a passive, what we call a GLUT, which is effectively just a passive glucose carrier. It works either way, but since we're building up glucose in here, that movement is mostly outward, and we get reabsorption of glucose. Yay! All right, now, quickly back to this. One thing I like to have students think about to make sure they understand this is to imagine, I'm telling you that this works because even though glucose is a little more likely to be here, sodium is very unlikely to be here. It's almost like saying if you roll the dice, a glucose will be here on a roll of 1 through 3 and here on 4 through 6. But sodium will only be here on a roll of 1 and here any other number, 2 through 6. So if I roll a glucose die and a sodium die, I'm a lot more likely to get numbers that'll move them through that way. That may not have made any sense. Don't worry about it. But what if this pump weren't running? If I wasn't running this, so the sodium wasn't getting transported out, sodium would be coming in, but now this concentration would start to get bigger, and eventually it would be the same as this one. What would be happening if sodium had the same concentration inside as outside? In that case, sodium would be just as likely to be here as here, so no difference for them. And glucose would be a little more likely to be here than here. So you'd be more likely to get glucose and sodium together on this side, which means it would be slightly moving outward. That's what I mean when I say that this movement of glucose relies on this pump working, because that's what makes sure the sodium concentration in here is low. That's where we're getting the energy for this secondary active transport. We use ATP here to make sure this concentration is low, and then by making sure glucose and sodium have to go together, we use this sodium concentration gradient to bring the glucose in, if you want to think of it that way. All right, so now we've talked about reabsorption of sodium and glucose here in the proximal tubule. Our third one, water. How are we going to reabsorb water? We have no kind of powered water transporter, and we have no water sim ports. There's no way to do secondary active transport of water. But fortunately, I don't need to. Remember, water moves by osmosis. Water goes where there's more solutes. Think about what I've done with these two solutes. I've moved sodium and glucose from here to here. So, what has that done to the osmolarity here if I've added more solutes out here? Osmolarity here has gone up. If I've removed solutes from here, osmolarity here has gone down. Water goes toward the higher osmolarity, which means now water, mostly between the cells, is going to be drawn from the lumen here because it's following the solutes, that osmolarity. That's actually the only way I can make water move around in the body, by changing osmolarities. But by moving those solutes through here, by reabsorbing solutes, the water will follow by osmosis. So I've reabsorbed sodium, glucose, and water. Yay! Now, one other point of interest on this. You may know that people with diabetes often end up with extra glucose in their urine, whereas normally we try to reabsorb all the glucose. One sign of diabetes can be glucose in the urine or extra urination, peeing out a lot more than you would expect. Let's think about why that might be. So here we're doing secondary active transport of glucose. When I filter, let me go back to this diagram. Here, when I'm filtering solutes, that includes some amount of glucose. And the glucose can be reabsorbed here by SGLTs. What I just did on this diagram, that's going on here. So I'm taking glucose out. But if my blood glucose is very high, I only have so many of these SGLTs. So if I've got a lot of glucose in the lumen, these may all be busy, and some glucose may get past them all. Any glucose that gets past them is now in here, and there are no more glucose transports anywhere else in this urinary tubule or the collecting duct, which means that any glucose that gets past the PCT is going to show up in the urine. So if your blood glucose gets high enough, you'll not be able to reabsorb it all here, and some extra will show up here. If you looked at your urinary glucose, it would be effectively 0 up until your blood glucose hit about 300 milligrams per deciliter. Just for reference, somebody who's not diabetic should have a fasting glucose of 100 or less. So if it gets to about high 200s, maybe 300, you're going to start seeing glucose showing up in the urine as some of it just doesn't get reabsorbed. Now let's think about the other symptom of diabetes, producing extra urine. Why would I produce more urine if I'm diabetic? Well, if the only way to reabsorb water is by osmosis, and in osmosis water follows the solutes, if I end up with extra glucose remaining in the urine, that means I've got a little higher osmolarity in the urine, which means a little more water is going to stay in here. You could think of it as the glucose holding some water osmotically. That extra water means extra urine volume, which means I'll pee more. So that's why sometimes diabetics have polyuria. They urinate more. It's because if their diabetes is not well controlled, their blood sugar is high enough that not all the glucose gets reabsorbed, which means it holds some water with it osmotically. Okay, so that's reabsorption of sodium, glucose, and water in the proximal tubule. All right, now let's talk about reabsorption in the distal convoluted tubule and the collecting duct. So up here I've just sketched out the nephron, Bowman's capsule, PCT, loop of Henle, DCT, and collecting duct. We're going to talk about the loop of Henle, that reabsorption, in the next lecture when we talk about fluid balance in the body. You'll learn more about that there. But right now let's look at DCT and collecting duct. So let's start with the DCT here. We'll draw in one of the cells of the DCT. This is what's known as a principal cell. There are several kinds of cells here. You'll learn about some of what they call intercalated cells when we talk about acid-base balance. But this is a principal cell. The principal cells of the DCT have sodium-potassium ATPases in their basolateral membranes. So that's moving the potassium in exchange for sodium out. Notice that 3:2 ratio. That's going to be important here. And they have sodium channels, which means sodium is coming in. As this lowers the sodium concentration here, that brings sodium in this way. So these are reabsorbing sodium, kind of like we did in the PCT, same idea. Now, in the PCT, though, we had potassium channels up here, which meant the potassium just sort of cycled. Here in these principal cells, the potassium channels are down here, which means as I'm pushing potassium into the cell with that pump, concentration of potassium rises here, which means potassium is moving into the lumen. Remember, this is the inside of this tubule. This is going to be urine. So here in the DCT, we're actually secreting potassium. Potassium is moving from the body, this is where the blood is, into the cell and then through it into the lumen, where it's going to be lost in the urine. So these principal cells reabsorb sodium and secrete potassium. Now, think about what that's going to do in terms of water. We said that water follows the solutes, which means that when I move solutes from one side to the other, water should go with them. But here I'm moving solutes both this way for sodium and that way for potassium. So which way will the water go? Well, take a look at the numbers. Every time I do this, I move 3 sodiums to here and 2 potassiums to here. So overall, if I moved 3 ions that way and 2 ions that way, which side had an osmolarity that went up? Looks to me like overall this side is getting more ions, 3 sodiums to here, then I take 2 potassiums to here. Overall, I've still gained 1 ion here and lost 1 ion here, which means the overall effect of this is that water moves from here to here. Now, that's fine and good, but let's briefly talk about a hormone that affects it, and that is aldosterone. One of aldosterone's big effects here is to insert more pumps in the basolateral membrane, more sodium-potassium pumps, and insert more channels into the apical membrane. So aldosterone does the same thing, just more so. I add many more pumps and I add many more channels, which means I'm reabsorbing more sodium and secreting more potassium. So aldosterone causes me to reabsorb more sodium and secrete more potassium. So if I'm doing that more, what about water? Well, the more of this I do, the more water I'm going to reabsorb. So aldosterone causes me to reabsorb more water. That means I will have less urine produced and more water kept in the body. That extra water kept in the body is going to add to my blood volume, which will tend to raise my blood pressure. So aldosterone has a fairly strong blood pressure increasing effect by increasing water reabsorption here in the kidneys. Okay, now, and keep that in mind, we're going to come back to that. Now let's talk about vasopressin. Vasopressin is going to be an issue mostly here in the collecting duct. So let's take a close-up look at a cell in the wall of the collecting duct. So in this case now the lumen is over here. This is the apical membrane. This is the outside. We're looking at something in this wall. Now, here in the collecting duct, we're primarily going to be worried about water. And what I'll tell you, without explaining it right now, is that there's a high osmolarity out here. Don't worry about why. We'll get to that next lecture. So, if the osmolarity is high out here, that means water will tend to be drawn toward that higher osmolarity. But there's something interesting about the cells of the collecting duct. First, the junctions between the cells are tight junctions, which means water cannot pass between these cells. Second, these membranes have more cholesterol in them than usual, which means that water really can't easily move through these cell membranes. So this thing is largely waterproof. Water can't get to this high osmolarity. It would if it could, but these membranes are waterproofed. So how are we going to get water through there if we need to? Well, we mentioned this briefly earlier in the class, but there's a kind of channel that's for water called aquaporins. Somebody won a Nobel Prize for discovering these. We find aquaporins in the basolateral membranes of these collecting duct cells. So this side, while water can't go through the membrane, it can go through the channels. So this side is permeable to water. But that doesn't allow water to get from here to here because water still has to get through this membrane. And normally we don't have aquaporins in that membrane. What we do have is vesicles, little membrane bubbles, which have aquaporins in them. Now again, that doesn't let water get through this membrane. But when this cell is exposed to vasopressin, something interesting happens. Under the influence of vasopressin, these vesicles move up and join with this apical membrane so that their aquaporins are now part of that membrane. And now, water has a path through. So this is what vasopressin does. Vasopressin causes these vesicles to move up and join with this membrane, thus inserting their aquaporins, making the cell permeable to water. So, if there is no vasopressin present, these collecting duct cells are not permeable to water, water will not be reabsorbed, and more water will end up down here coming out into urine. But if you have vasopressin, water can leave the collecting duct, going back into the body, because now it can go through those cells drawn out by the higher osmolarity. So we'll say vasopressin causes increased water reabsorption. That will lead to less urine and higher blood pressure as that water returns to the body and is added to the blood volume. Now, the question then usually comes up, so what tells me whether to make vasopressin or aldosterone? Aldosterone we're going to get to in the next lecture, or possibly the end of this lecture. But vasopressin, largely, the main signal for vasopressin is when your blood osmolarity gets high. In other words, when you've got more solutes than usual in your blood, that's a signal to your pituitary gland to make vasopressin. What vasopressin does is take water that would be lost in the urine and bring it back to the body. So if I'm adding water back to the body, that's going to help lower my blood osmolarity, which will then, that becomes a negative feedback system. If high osmolarity causes vasopressin secretion, vasopressin moves water back to the body, which lowers osmolarity. Now, in the next thing we talk about, in the third part of this lecture, we're going to talk about something called the renin-angiotensin-aldosterone system, which has a lot to do with aldosterone and a little bit to do with vasopressin. Right now, what I want you to make sure you know, though, is that both of these hormones, aldosterone and vasopressin, cause me to reabsorb more water from the urinary tubule back into the body. So, back into the body. That means less urine, but higher blood pressure. Keep that in mind, and you'll get the next part just fine.